Okay, so we're going to look at Unit 6A. So this is where we start looking at uh, different types of statistics, more continuous distributions rather than the histograms and bar graphs and pie charts that we were looking at before. So we view these kind of as continuous curves, and we'll talk about some of the measures of the center in this section. And I'll show you how to do those on StatCrunch, which is a little bit easier than doing them by hand. So some of the examples that they have in this section are done by hand, but StatCrunch is a really nice tool that will allow you to kind of skip over that tedium. So the distribution of a variable is all the way its variables are spread over the possible variables, and we can display it with a table or a graph. The bell curve is a common one. That's also known as a normal distribution, and we'll be looking at that in either 6b or 6c. So measures of center. A lot of times in high school, you take a lot of you think about the average or the mean of something as a good measure of center. But for a lot of these, so the means are the most common. You just add up all the values and then divide by how many things there are. There's also the median, and for a lot of statistics, this is the more relevant measure of the center because it is more resistant to outliers than the mean. So there's an example where we'll see what that means in a minute, but the median just is what happens when you organize the data from smallest to largest and pick the number in the middle. Sometimes there's a single number in the middle. If you have an odd set of data, say your data is 1, 3, and 5, your median would just be 3. But if you had 4 data points, let's say, 1, 2, 3, 4, then you would have 2 numbers in the middle, 2 and 3, and you'd have to take their average, which would be 2.5. So there's 2 cases for the median. The mode is just the most commonly occurring value. If there is no most commonly occurring value, there's just no mode. You can also have multiple modes. So find the mean, median, and mode for these prices. So let me show you how you can do that on StatCrunch. So if you go to your MyLab Math home through Canvas, you can just click StatCrunch, and it brings this up, and then you can just visit the StatCrunch website. So open StatCrunch, and there it is. So we could just type in all these values in a single column, 1.09, 1.29, 1.29, didn't hit enter, 1.29 again, 1.35. A lot of times when you have examples from your textbook, there is the ability to just open the data directly into StatCrunch without having to type it, but since this is on a PowerPoint slide, that's not so easy. The formatting is a little weird, but not so many values. Okay, so we've got 8 values there in variable 1. So the way we find what we do is we want to go to stat, summary stat, and we typed them in by column. So just select the variable, and then there's all these different statistics that it'll measure from it. So let's just do the ones they asked for. So you have to hold down Control when you're selecting these things. But let's see. So the mean, that's the first one. And then holding down Control, I'll also select the median. And then see if we can find mode. There it is. So there's our 3 measures. And just click Compute, and we get those statistics right there. So we get, I was hoping it would get a little bigger. There we go. 1.41 for the mean, 1.37 for the median, and 1.29 for the mode. So let's see if that's what happened on here. So the mean, yep, they got 1.41, and they just did it the by hand way. Add them all up and then divide by the total number of things there are, which is 8. The median, they just sorted from smallest to largest, and we get the case where there are 2 numbers in the middle, 1.35 and 1.39. So if you average those, you'll get our answer of 1.37. And the mode is just the most commonly occurring. If you browse through the data, you see all the numbers are unique except for 1.29, which appears twice. So that's why 1.29 is the mode. But anyway, if you have a big data set, you're never usually going to want to do these by hand. You're going to want to use some sort of spreadsheet functionality, and StatCrunch is a really good one, especially because a lot of the problems that are on the homework, you can open the data directly into StatCrunch. Okay, an outlier in the data set is a value that's either really high or really low and doesn't really fit in with the data. We'll talk about that in terms of, right now it's like, well, what does really far and really low mean? Well, kind of how spread out your data is described by the standard deviation, and once we understand that, we'll be able to give a more technical definition of what an outlier is. Usually, a lot of text will say anything that's above or below 2 standard deviations. That 2 standard deviations above and below the median captures 95% of the data. If you did 3 standard deviations, that captures 99.7% of the data. So anyway, yeah, so if this is a set of contract offers, clearly almost all of them are 0, so most of the contracts are not worth much. And this is a good way where you can think about the median and the mean. What would the mean of this data be? The mean would be 10 million divided by 5. So that would say on average the contracts are worth $2 million. But if you picked a contract at random, if you organize this data, there's 5 points. The number in the middle is 0. So although the mean is $2 million, the median is 0. So those measures of center are very far apart, and that's because we have a serious outlier here. So yeah, mean 2 million. So usually outliers pull the mean in their direction. So since you have a really big mean here, the mean is going to be pulled closer to it than the median will be. The median, that's why we said earlier, it's resistant to outliers. Because the median there would have been 0. Okay, so a newspaper surveys wages for assembly workers in regional high-tech companies and reports an average of $42 per hour. The workers at one large firm immediately request a pay raise, claiming that they work as hard as the employees at other companies, but their average wage is only $36. The management rejects their request, telling them that they are overpaid because, in fact, their average wage is, in fact, $48. Can both sides be right? Explain. So let's think about this again. Newspaper surveys wages for assembly workers. I don't know. This is kind of funny. I mean, if the data's right, so they're using the word average, and so far for statistics, we've only used the words median and mean. So if one is using the word average to mean mean, and the other is using the word average to mean median, then certainly this could be possible. So, right, if you have some outlier employees that are paid very, very high at this company, then as we saw in the previous example, the mean could be $48, whereas the median could only be $36. So my only question is, what do they mean by average wage? Because in the text, they haven't used the word average as we traditionally do. A lot of times we traditionally interchange average and mean, but I think in this text they're using mean exclusively. So I think this would be one of those differences where we have the median being 36, but maybe the mean being 48. That would be the possibility that occurs to me. So let's see what they say. Yeah, so if they're using different definitions of the average. Yeah, so that's exactly what we're talking about. Yeah, so if you have a high outlier, then you could have the mean being 36 or the median being 36, but the mean being 48. And it's pretty much the exact same setup as the contract dispute that we just saw. Okay, shapes of distributions. So how many peaks it has, those are sometimes described with, a Greek prefix uni and then the word modal. So this is unimodal because it has 1 peak. A distribution with 2 peaks would be a bimodal distribution that we see here. It has 2 distinct peaks to it. Notice that, so the next thing that I think they talk about is symmetric. So this top graph here is symmetric, and we see how the histogram, we're just drawing the curve essentially to model it on both of them. So since this is pretty symmetric, meaning if you draw a line through the middle, it kind of looks like a mirror image to the right and the left, we would say this is symmetric. But this bottom one we would say is skewed. And the way you describe the skew is actually toward the tail of the distribution. where you see more of the outliers. So this would be, I mean, it's bimodal, but you might say that this is skewed right. If we have an example with some, you can talk about the skew of unimodal distributions as well, but it's not toward where like the area is, it's where the tail points is how it's described as being either right skewed or left skewed. Yeah, symmetric, again, if the left half is a mirror image of its right. In this case, the mode, mean, and median are all actually the same value. But yeah, so then where you have more spread out on one side than the other, we say the distribution is skewed, and we can talk about being right skewed or left skewed, depending on where that spread is. So here's the skewness. Notice a lot of people see the hump to the right, and they assume this would be called right skewed, but it's actually where the tail is, because that's where the outliers exist. So that would pull your mean to the left. So for that reason, this would be a left skewed distribution. And distribution where the outliers are at the right, this would be known as a right skewed distribution. Notice the mode is the highest point of the curve. The median would actually divide the areas, where the area to the left of the median is equal to the area of the right of the median. And then the mean is as is traditionally defined. Yeah. So there we go. Symmetric if its left half is a mirror image of the right. Left skewed if the values are more spread out on the left, or the tail is to the left, where you would see outliers, and right skewed if the values are more spread out on the right side. Okay, so for each of the following, state whether you expect the distribution to be symmetric, left skewed, or right skewed. Explain. Heights of a sample of 100 women. I mean, I think height is typically normally distributed, so I would expect that to just be symmetric. Number of books read during the school year by 5th graders. Well, you might expect more books as they go through the year if they improve at reading. So maybe there would be more books read. So if the books being read are to the right, being later, there would be more of them. So the skew, there would be fewer of them read at the beginning of the year would be my guess. But maybe there's fatigue that sets in and students don't want to do as much as it gets close to the summer, so it could be completely the opposite. The only indication that I would say maybe it's left skewed rather than right skewed is just based on their age, since they're young. But yeah, so that, I mean, that one, I could see maybe two rationales. C, speeds of cars on a road where a visible patrol car is using radar to detect speeders. Well, we would expect that to be, we wouldn't see people driving as fast there, right? So that would be right skewed, because people that are driving faster are more likely to be caught, and you wouldn't expect that to be happening. So I'm going to say symmetric. B, I could really go either way. I was leaning toward left skewed, and for C, I was leaning toward right skewed. Okay, distribution of heights of women is symmetric. Yeah. So it's well known. The distribution of the number of books read is right skewed. Okay, so it's how many they read. Okay, so some of the students read many more, so it's more. So the outliers are the students that read lots of books there. Okay, I was thinking about that wrong. I was thinking about it in terms of during the year, just the total number of books being read. So I was a bit mistaken, but again, these examples can be kind of vague. And then drivers usually slow down, right? So yeah, the distribution of speeds is therefore left skewed, with a mode near the speed limit, but a few cars going well below the speed limit. Oh, so they're saying cars slow down too much. Yeah, so maybe there's not high outliers either. Anyway, so I kind of got B and C backwards. But yeah, I would just think most cars were driving slower, so if you had cars that were driving really fast in front of the police, maybe because they didn't notice, that would be the outlier. Anyway, again, these things are kind of vague, but if you actually had hard data, you wouldn't have to try to infer what the data would look like. You can just look at the data and come to your own conclusions. Okay, variation, how widely the data values are spread out. So if they're clumped together in a tight curve, as we see to the left, that's low variation. Moderate looks more like it's just kind of normal. And high variation, it's going to be flatter, so kind of stepped on a little more and spread out. So not as much in the middle. So yeah, there's some basic examples illustrating variation. How would you expect the symmetry and variation to differ between the times in the Olympic marathon and the times in the New York marathon? Well, the New York marathon is an amateur event, right? So you would expect a higher variation there because you're going to have some really good runners, and then you're also going to have some really bad runners. Whereas in the Olympic marathon, everyone there has to qualify, and so all the runners are really good. So you would expect that to be a much lower variation because it's all world-class runners. So the times should not be spread out. Yeah. So as we see, this is pretty much the explanation. Olympic marathon only has elite runners that are clustered not far above world record times. New York allows any kind, so the variation among the times is going to be bigger. There's more variation in New York than there is in the Olympic marathon. All right, well, that does it for this section. Again, some of the examples may be a little vague when they're only words, but if you get your hands on some data, you can always analyze it and get a good feel for it that way. And we'll see some more examples of that in the next couple sections.